So the fourth and final summary sheet that we're going to do is going to be the slowing down with constant acceleration. So similar to what we did with speeding up, what do we know about the velocity? Well, we know that it's going to be changing. And what do we know about the acceleration? We know that it is going to be a constant. Even if we don't know what it is, it will be a constant number. So we can fill those in up at the top. So the velocity is changing, the acceleration is constant. Okay, so another time to really focus in and be attentive, and this is very detail-oriented again. So when a car is slowing down, the position, distance it is at is changing, and the velocity is also changing. So if it's slowing down at a constant rate, that means that the velocity is changing by the same amount in each time interval. But now it's heading towards slower, and it's heading towards zero, and it's getting slower and slower and slower. So it's going a shorter distance each time interval. But the distance isn't really not changing by a constant amount. So initially, when it's going at a faster speed, it's going to move a large distance. And as it slows down more and more, it's going to move a smaller distance and a smaller distance until it reaches a velocity that would be like close to zero, where it's barely moving at all. So let's look at the numbers and graphs. So thinking about the data here, I've got an acceleration of -4 meters per second squared. And this time I started the object moving at a velocity of 24, and then it reduces by 4 and reduces by 4, reduces by 4, reduces by 4. And for the distance, I decided to start it at 0 and move it in the positive direction. So this was going to be my red line. So it moves by 24, and then it moves by 20, and then it moves a little bit more and more. So we end up with something that looks like this. And then when we graph this, it moves quite a bit, not moving quite as much, not moving quite as much. And as you get farther and farther along the time axis, you can see that it's hardly moving at all, and it's almost flattening it out. It may not be completely flat, but it's heading towards being a very flat horizontal line. So it starts out very steep and then ends up being very flat. Whereas the velocity starts out at some higher value and heads towards zero, okay? So in this case, when we're talking about acceleration and we look at this slope here, this is a negative slope, right? So it is a negative acceleration. And because it is moving in the negative direction, it is actually, or not moving in the negative direction, sorry. It's moving in the positive direction and it's slowing down. That's a positive times a negative, which equals a negative. So you have a negative slope on your acceleration here. So for the blue line, I believe I did the same thing. So the blue line, I didn't actually make more data, but I considered basically the same thing, but only we're in the negative area. So we're starting out at some distance and we're going quite a bit distance initially, and a little bit less, and then it starts to flatten out. And here we start at some velocity and it's negative because it's in the negative direction. And it also heads towards zero. Remember, negative velocities doesn't mean it's below zero because you can't have a velocity less than zero, but the negative indicates direction on this. So this is what your distance time or position time, they will have the same shape, would look like for slowing down. And this is what your velocity time will look like for slowing down. Note that these are different than what you have for speeding up, okay? So forces and equilibrium. So what do you think about those? So do we have balanced or unbalanced? And what about our net force? and what type of equilibrium. So hopefully you recognize that they're unbalanced forces, that the net force is not equal to 0, and that there is no type of equilibrium for this type of movement or motion. It's slowing down with constant acceleration. So looking at our free body diagrams and our ticker tapes. So for slowing down, what happens to the dots? Well, they should get closer and closer together as time goes on. So if we start over here on the left-hand side and the motion is going to the right, like the arrow's directed, it's moving this way, the spacing is going to start out farther apart and then it's going to get closer and closer together. So considering the free body diagram, we can recognize that the overall acceleration for slowing down is going to be in the opposite direction of the motion. So if it's moving to the right and it's slowing down, the direction of the acceleration is going to be to the left. And so you basically have the same thing on the free body diagram. The overall net force has to be towards the left also, okay? So however you draw it, you need to have an overall net force to the left. The same thing's going to be true if you have the object that starts on the right and moves towards the left. So the dots are going to get closer and closer together in the direction of motion, and the acceleration will be to the right, so the overall net force on our free body diagram must also be to the right. So you should end up with something like this. So for motion to the right, your dots are getting closer and closer together as you move along the ticker tape, and your free body diagram indicates that there is an overall net force to the left, which is the same direction as acceleration. And for the motion to the left, it is exactly the opposite. So you start over here on the right with the dots, they get closer and closer together, and your overall net force is going to be to the right. And just like when we talked about some of the other free body diagrams, there can be vertical forces, and most likely there are, because as long as we're on Earth, we're always going to have gravity acting down on us. But they're going to have to be balanced in the up and down direction. But the important thing for this type of motion is that your net force is going to be opposite the direction of motion. So here is my overall sheet with the entire summary on it. So you can compare anything that you still need to note. And again, this speeding up and slowing down and trying to keep straight which distance time graphs look, what they look like, and what the velocity time graphs look like is one of the things that really students really struggle with. And this is so important, okay? But these 4 sheets is a huge summary of everything that we've learned and so much that we know, and it ties everything kind of together. These are actually some of my favorite sheets because as we work through them individually, we're like, oh yeah, that kind of makes sense. And yeah, I know that. And yeah, I learned that. I think it's really helpful for students to do something with these that will help you. Make yourself some Quizlets. Make yourself some little flashcards. Do something to try to get ingrained in your own mind what these curves look like, what the lines look like, and whether they're slowing down, speeding up, constant velocity, at rest, because that will behoove you as we're going into the next section talking about graphs, okay? When we just focus on the graphs and are not thinking about all this other stuff, and you're given a graph and you're asked to look at it and say, what does this graph represent? You're going to very likely say, oh, I don't know. Well, if you go back and look at this information, hopefully you will recognize that you do know, and that this will help you. So keep these sheets somewhere where you will not lose them. If you separate them and put them in sheet protectors, that could be really useful to you. But these are probably the most helpful in kind of working your way forward through some of the rest of the material that's coming out. Okay. All right, so I will join you again in the next section where we're talking about graphing.